Good morning. Welcome back to Physiology 452. Today I'm going to start back, actually, in the previous lecture I've gotten some feedback from students via email and such with some fundamental types of questions. And really, they're not really surprising to me that these occur. A lot of it has to do with definitions, and in particular one that stuck out was, what is the calcium channel? That's probably where we come to problems in people learning different aspects of biology. I don't remember where I read it, but somewhere I read that the average biology student runs into more new words per lesson than the average foreign language student. And I believe it's true. I mean, the abbreviations and jargon that is used in biology is enormous. And it comes from several types of principles. The fact is that various disciplines have oftentimes merged and come to the same points. So you end up with terminology that's a bit mixed. So a lot of times I will be talking about the sarcolemmal calcium channel, or the voltage-gated calcium channel, or the dihydropyridine receptor, or the L-type channel. These are all basically referring to the same thing in the final analysis. And the problem arises is that all these are terms that you're going to encounter should you read the literature as you go on in your professional careers. They're all used from different things because different parts of these things were discovered through different methodologies and from different disciplines. Electrophysiology is a very distinct branch of physiology or biological sciences in that it deals with electronics and current, and really came out of advances in electrical engineering from as long back as Volta and such. Bioelectricity versus inorganic electricity, or organic versus inorganic life. This is what Volta was trying to do with his pile and showing that legs can contract. And of course, Einthoven was using what was at the time the very most advanced electronics to measure the EKG in the heart. And this continues to this day. A lot of what we know about channels are just basically little pores that conduct one ion specifically through the membrane. Comes from Hodgkin and Huxley and their background, which was working in radar and electronics during World War II, and they applied this to biology. So the terminology from that comes very, very steeped in terminology of conductors, conductances, channels, pores, permeation. These are sort of physical phenomena associated with, say, semiconductors or vacuum tube electronics at the time. At the same time, people were working on drugs and drug binding and their effects on things and the fact that they bound specific proteins. And so one of these classes of drugs happened to be the dihydropyridines. And the proteins that it binds to are the dihydropyridine receptors. And this, so eventually these branches collided. And we know that the dihydropyridine receptors are, in fact, a class of calcium channels. So calcium channels are, like all channels, named after the ion they conduct. Any pore that conducts calcium is a calcium channel. Now, on this diagram here, and this is kind of why I'm starting in the middle of the smooth muscle, you can see several channels on here. We see our voltage-gated calcium channel. In heart, skeletal muscle, this is our L-type calcium channel, and it's a dihydropyridine receptor in the heart. And in skeletal muscle, this is this calcium channel. While it is, in fact, a calcium channel as a protein in structure, its actual function has been modified so that its movement of this calcium channel physically not permeation of ions, that is connected to this other channel here, ryanodine receptor channel, or ryanodine receptor. Well, as you might guess, that comes from a different thing. It's also called the intracellular calcium release channel. Ryanodine was a drug that specifically blocks this channel, and today, ryanodine receptor helps us identify exactly which class of proteins we're talking about. Because as it turns out, there are other calcium channels in the cell membrane that are gated by a different mechanism, and these would be the inositol P3, IP3, inositol triphosphate calcium channels. And they bind inositol IP3. They also bind calcium, and they are active to release calcium from the stores. So they're yet another calcium channel. Again, IP3, because that's their ligand, so coming from a biochemical area. And those are at least some of the channels you'll actually encounter. There are other calcium channels as well. There are T-type calcium channels, N and P. So there are a great number of calcium types of channels. Right now, for the sarcolemmal channel, we're just going to treat that as though all sarcolemmal calcium channels are, in fact, L-type for the moment. So that's our voltage-gated one. It opens in response to changes in depolarization and it's at the cell surface. In the skeletal muscle, its conduction is not so important in giving you excitation, contraction, coupling, because its gating is. There's actually a physical connection between that and the intracellular stores. Whereas in in cardiac muscle and in smooth muscle, you need diffusion of the calcium to this. So it was a bit of confusion from the emails I got. I wanted to try and straighten that out and to really emphasize that this is biology. We have a lot of words for basically the same thing, although there are subtle distinctions because of the history behind how that particular class of proteins was identified and treated and which disciplines it came from. We have a lot of other calcium uptake and release mechanisms. Circa, a general here, is our ATP for uptake into stores. And of course, sodium-calcium exchange. 3 sodiums in for every 2 calcium extruded. That's how it works. These are exchangers and pumps. Pumps use ATP. Exchangers use the gradient of one ion to facilitate the transport of another ion. So in the cell, we have this going on for all these muscle types. And in smooth muscle, we particularly have distinctly the IP3 gated. We have this much less regular structure, longer diffusional distances in general. IP3 mediated mechanisms, although we still have the possibility for all the others. And so that's an important thing to remember, that it has basically, you can find in smooth muscle cells all the stuff that's in cardiac and skeletal, pretty much, but also you have these IP3 release pathways. And again, that regulation of the cross-bridge cycling is different. It's no longer done directly by calcium binding to tropomyosin. Instead, myosin light chain kinase actually puts a phosphate on the myosin and allows it to cycle. So myosin kinase, I'll just emphasize that, not troponin and tropomyosin interaction. In smooth muscle, it regulates cross-bridge formation. That gives you some advantages because you can stop this at any point in the cycle. You can remove things either in this relaxed state, in the tetanic state, or the Riger state, or in the relaxed state. And so you have several places you can arrest the system. What sort of advantages would that give you? Well, it gives you the advantage of changing how long you're going to generate force and how much energy you're going to use for it. So normally in a muscle contraction, we get what's known as phasic contraction. So, you know, skeletal muscle is basically all phasic. You get a calcium burst, you get an excitation, you get a twitch of your fiber. You know, it follows that cross-bridge phosphorylation or cycling, and you generate some force, and then as calcium goes down, it goes back. Well, in order to generate, say, a long-lasting contraction, as you might want to for smooth muscle, for instance, you want to keep some muscles contracted pretty much all the time, except for when you want to suppress that. You know, so various sphincter muscles that allow the evacuation of various fluids and such from your body, you want those to remain in a tonic contraction. So you want them to contract, stop, and you don't want to be wasting all that energy of constantly cross-bridge cycling that you have in, say, skeletal muscle to develop tetanus. And so you could cause that to develop what's known as tonic contraction. So phasic and tonic, two important terms. Phasic just means that it's a transient type of behavior and results from transient type behavior of the calcium current. Tonic meaning basically it's like a latch. You know, you switch it on, switch it off, and you go into a tonic or long-lasting type of behavior. And so, just to re-summarize here, skeletal muscle, you've got direct activation of the SR. That's one of the things that really makes it distinct, say, from cardiac muscle. And it sums its stimuli and can produce tetanus. In cardiac muscle, big thing is calcium-induced calcium release, and is dependent on the extracellular calcium entry to trigger both release from the SR stores and also directly to bind to troponin and cause muscle contraction. And instead of being sensitive to the number of stimuli that it has, it is sensitive to action potential, shape, duration, and on a longer time scale, rate of beating. We'll talk about that quite a bit more. And then smooth muscle contraction is sort of the catch-all for all these smooth muscles. It has myosin kinase in charge of it. So instead of regulating cross-bridge interactions at the level of troponin, it is regulating it at the level of myosin, and it can involve some additional calcium release pathways, most importantly the IP3, or inositol triphosphate dependent pathways, so that extra channel there. So now the question that I kind of expected but didn't get was, I refer to these action potentials as initiating events and got no questions about them. But today's lecture is, and that's hopefully because everybody's been looking at notes ahead of time, the generation of the cardiac action potential. So where does an action potential come from? What do I mean by a cardiac action potential? And how is it distinct, say, from a neuronal action potential? So we define an action potential as a regenerative event. That is, it's something that fires in an all or none fashion at some point and triggers a preset set of events. And it arises from current flow. That is, charging and discharging of the cell membrane capacitance. So currents cross a membrane, and in this case the currents are carried by ions, not by electrons as in electronics. They're carried by sodium and potassium, chloride, calcium. So they're carried by charged ions in solution rather than by electrons as they are in, say, wires. And it's this balance of current flow also that gives you what's known as the resting membrane potential. So your cells don't sit there just at 0 volts with nothing going on. They have a resting potential. They are polarized. And so that leads us to sort of this concept of polarization. Polarization is important. It helps us balance out things, how things work in the cell. It helps us maintain cell volume. And it does this by helping us balance a lot of things. We have a lot of stuff that goes in and out of a cell. And it goes in and out through channels and through transporters. And so the example in your book from the readings that I gave you is about volume homeostasis. So volume homeostasis is how does a cell keep itself from exploding? A cell has stuff on the inside and it needs to keep it on the inside. It has stuff on the outside it needs to keep on the outside. One of the things that water does is moves to an even concentration between the two. And so we have what's known as the pump leak model that goes on with volume homeostasis. And there, it's a variety of things that go on. We have, amino acids that we need to bring in to build proteins and stuff, sodium and glucose. We have waste products, hydrogen, lactic acid, various other things. Every time we cycle through an action potential, we have to move calcium out, sodium back in because calcium has come in through a channel, and things like that. And we have a need to transport calcium electrogenically. But probably backing all this up, this is fairly minor, okay, in terms of energy. Backing all of this up pretty much is the sodium-potassium pump. It's really the workhorse of the cell membrane. It provides the energy to develop the gradient. So it passes 3 sodiums out for every 2 potassiums in. And when it does that, you're moving net number of charges out. That has to be balanced. And so that can either be balanced by potassium moving out or chloride moving out. So we have 2 potassiums, 3 sodiums, 2 potassiums, and that drives everything. So this fact that it's low sodium inside drives this sodium amino acid transporter. So sodium is coupled to an amino acid, it net moves current in, sodium and glucose, net uptake, sodium in, pumps hydrogen out, that's an exchanger, so co-transporters, exchangers. This one is a pump because it has ATP, even though it exchanges some. Same thing with this. So you will find the term sodium-potassium exchanger sometimes in the literature. It should be a sodium-potassium ATPase pump. But the net charge of constantly moving 3 positives out means that you have to move the membrane progressively more and more negative. As you move it more and more negative, then potassium will have, it'll be high on the inside, low on the outside. It will tend to diffuse out, and it will reach its equilibrium. Now, what you see here is that there's no transport for chloride. So that means that chloride is always at its Nernst equilibrium, or just about, in the absence of any transporters. And so that tends to keep chloride, if this is minus 60 inside, relative to ground outside, or 0 millivolts, chloride has a negative charge. If you have a negative charge in a field, with think of those Van de Graaff generators you saw maybe in high school or in physics. So you have a negative charge and a positive charge, and you have a negative charge here, it's going to be repelled and move towards the positively charged side. Same thing, there's a net force on it due to this membrane potential. The electrical field on these chlorides will push them out of the cell until the chemical potential exactly equals the electrical potential. And so you end up with low chloride on the inside and high chloride relative on the outside. The net effect is that you've removed sodium chloride from the intracellular side of the cell. And that reduces the osmolality. And this is a diagram that we frequently tend to look at in electrophysiology. It has some important things on here. It has the Nernst potential for each of the ions. Now, the Nernst equation, we'll show that to you later, is something that is a conversion factor. It converts from the units of chemical energy in terms of concentration for charged particles into electrical separation. So you have two forces working on them. One is the force of diffusion, because you have a concentration gradient, that's chemical. And then the other is these ions will be separated by a field, that voltage, and that is an electrical gradient. And since they have charge, it exerts a force on them. And when those two are equal and opposite, that is where there is no net movement across the membrane. Movement will still be random, but will still move across the membrane. And so what that system sets up is a balance. So it pumps the potassium out until you get down here to EK. That's where the potassium is going to diffuse in or diffuse out. And the resting membrane potential will be somewhat above this, because you'll also have, you have a conductance then for EK. Conductance. Everybody remembers Ohm's law, V equals IR, or I equals V over R. Now, when we have a battery in that sort of system, V is no longer simply the membrane potential. It is the sum of the membrane potential plus the Nernst reversal potential. So here we have the membrane potential. Okay, and we can stick an electrode in a cell. We do this all the time in my lab, pretty much every day. You stick an electrode in a cell, and you can control what that membrane voltage is. And so if you put it down here at EK, the voltage will exactly equal the potassium gradient. Similarly, if you go up here, remember you have sodium that's high on the outside and low on the inside. It wants to go inward. And so its reversal potential is here. You have to actually have a pretty strong positive charge on the inside in order to force sodium to go out. So for some typical concentrations, you have values here. And then you have chloride that sits somewhere in the middle. In this particular case, at minus 33. In your book, you may find it hard to find out why that's not at minus 60. That's because there's actually a transporter that goes on for it that's coupled to sodium and potassium in most cells. So the membrane resting potential, if you have these two conductances, or three conductances, is where the sum of the currents equals 0. And that will sit up around minus, in this particular cell type, 64.4. So you see these currents where they're inward, that means ions are moving from the inside to the outside for that net driving force, which is a sum of sodium, or for sodium, for instance, is a sum of the Nernst potential and the actual membrane potential. Similarly, the potassium conductance, usually high at rest, follows a line like this, and then you can sum all of these together and you get your net resting potential and your total membrane conductance. Those are probably pretty confusing. We'll be going over them hopefully ad nauseum here to do, but sort of from this first glimpse, in order to follow the arguments that go later, you need to know sodium is high on the outside of cells, low on the inside. Potassium is just the opposite. It's high on the inside and low on the outside. And that chloride itself is at lower concentrations on the inside. Calcium is a little bit funny. I suppose it should be. It's in the center of everything here, so why wouldn't it be more complicated? Calcium is at very low free concentrations on the inside of the cell. Very, very low. Sub-micromolar most of the time, or in the micromolar range. That's free calcium. If you actually measure the total calcium in a cell, it can be quite high. And that's because calcium as an ion in solution is very low, but most of it is bound to intracellular proteins. Calsequestrin, it can be sequestered as apatite crystals in the mitochondria, it's sequestered there. It's bound to calsequestrin in the SR. So the difference between calcium-free concentration and total calcium is very, very different because of the numerous processes that bind calcium. So we talked a bit about, I said this is is related to volume, this idea of osmolytes. And in your book, it talks about volume regulation. And so what a cell does, with, for instance, red blood cells, as they go through your circulation in your kidneys, can encounter huge differences in osmotic concentrations. Well, that can either shrink or swell a cell and really cause enough deformation to lyse the cells. And so when a cell is exposed to a hypotonic medium, water flows pretty quickly across most mammalian membranes. It goes straight into the cell. That would create an osmotic pressure, which would tend to swell that cell against the cell membrane. When that happens, the cell has to dump internal solutes. So in order to dump solutes, it has to have a mechanism to do that. The most common ones are through potassium and chloride. If you've got high potassium in there and you've got enough chloride around, you can afford to dump some extra and get closer down to your reversal potential. That can be done by opening potassium and chloride channels, or it can be done through KCl co-transport. In other cells, something that can do, particularly in desperation, is that it can dump organic solutes. Cardiac muscle cells, for instance, when exposed to hypovolemic or to hypotonic shock, can lose taurine and a host of amino acids. And these amino acids are lost. It does impair some of the metabolism of the cell. But if they're in a rich enough milieu, you can reuptake your osmolytes, and then you see this post-volume decrease followed by a volume regulatory increase. Similarly, if you shrink a cell, you have cytoskeleton there. You can actually lyse a cell through hypertonic means as you pull against that and you try to dehydrate the cell too far. The response of a cell to that is to add osmolytes in, and if it has access to them, it can uptake organic osmolytes in conjunction with chloride and potassium. This is what's known as a regulatory volume increase, trying to get that volume back up so you are at a normal volume. Another way is to simply allow sodium and the counterion chloride, not shown here, to diffuse in, so sodium chloride can enter. There is also an AK2Cl co-transporter. Yes, it transports for every cycle 4 ions in a fixed stoichiometry. 1 sodium, 2 chlorides, 1 potassium. And it is a co-transporter. They all move in the same direction. So it's like a long single file pore where I believe it's, I don't remember the exact order, if it's KCl, NaCl, or exactly what, but they enter basically in a fixed order. It's sort of like a long pore, switches sides, they come out on the other side. Another method is sodium hydrogen exchange, where hydrogen is extruded, sodium comes in. Usually that's coupled to chloride bicarbonate exchange, where CO2 goes out and chloride comes in, and you get that sort of thing there. So the idea is the cells have to maintain their volume and their shape in order to be a particular size. In fact, they have to do this all the time because you need to have an even balance. Even at rest, you have all these osmolytes inside. They do not have as much colloid osmotic activity outside the cell as they have inside the cell. You have a lot of things in a cell you want to keep there: ATP, proteins, amino acids, you just name it. There's a lot of stuff to keep inside there, that more than you have on the outside, so that there's a tendency for water to want to equalize its concentration on both sides of the membrane, and this leads to cells, if they have their metabolism stopped, that sodium-potassium pump to stop, they will explode, they will lyse. That's why cells swell when you have edema, when you have ischemia and other things. You just have an osmotic type of swelling that's intrinsic to cells. So you're constantly maintaining energy to maintain cell volume, not to regulate it. Regulation is in response to changes. Maintenance is something that's just going on all the time in the background. This constant movement of sodium out and net movement of chloride with it. So one of the things that's not clear in the book is that chloride in most cells is not sitting at its equilibrium. It's not at minus 65 like that first picture I showed you. It's maintained above its equilibrium by electroneutral co-transport. That for cardiac cells in particular, that NAK2Cl co-transporter is basically constitutively active at rest and maintains chloride up around minus 35 or so as its reversal potential. And this co-transporter is pretty important. It simultaneously moves 4 ions in a fixed stoichiometry, and it keeps that reversal potential around minus 40. And that's one of the things that maintains our cell homeostasis. Homeostasis is just sort of keeping the cell alive. We have to have that membrane reversal potential there because we have to keep sodium and chloride out. But that membrane reversal potential gives us the possibility of firing action potentials. As I've said a couple of times before, and I'll continue to emphasize, we have different types of action potentials for different cell types. We have really fast motor neuron action potentials, and the axons there, maybe less than a millisecond, very, very fast. Open and close, sodium and potassium, as you went through in 451. That whole process there. Then we have skeletal muscle. It's maintained a bit more negative for its resting membrane potentials. It's sitting down there. It doesn't want to be excited until it receives an impulse. Once it does, you have, again, maybe a couple millisecond long contraction. To get longer contractions, you need to have tetany or a series of stimuli to occur. Then we have the cardiac action potential, which, if it were drawn to scale, wouldn't even show up here, or these wouldn't show up relative to it. It's 200 milliseconds as opposed to these, which are on the order of 2 milliseconds or so. Very long action potential, which maintains some very important functions within it in terms of regulating cellular function. So it goes through the cycle. That cell membrane charges and then discharges, and even goes up and reverse polarizes and then repolarizes. And it does so fairly quickly in the beginning direction, but during the repolarization it takes a long time. And so you have to remember that action potentials come in a wide variety of shapes and sizes. There's no one size fits all in the body for that. Even though we refer to it as the action potential, there are numerous types of action potentials. Even within the heart, there are specializations. And the cardiac action potential is of particular interest because it is so long and complex and has so much to do with the control of cardiac function than the much shorter neuronal and skeletal muscle action potentials. But it still has some properties in common. In order to elicit an action potential in most cell types, you have to have a stimulus, unless they are spontaneously active. So in cardiac muscle, a stimulus has to arrive to bring it up to what's known as a threshold. And so this is, again, one of the important properties of an action potential, is this idea of an all or none threshold. So you if you get a small burst of current coming in, this is a stimulating current going in here, a small burst of current, you'll start to depolarize the membrane. So this is the membrane potential here, this is time, this is the current you're injecting. And so if you inject just a little bit of current, you get this depolarization, and then you turn it off, and really nothing happens. You go up a little bit higher, same sort of thing. It kind of wobbles along, goes up a bit higher, nothing happens. Then you hit a sudden and very abrupt point. And when you hit that threshold, all of a sudden, something happens. It fires an action potential. That is, all of a sudden something happens and this takes hold, and it goes up and up and up and up, and then goes through a preset of events and comes through. So we have our threshold. Once your threshold is gone, you depolarize. In fact, you go through an overshoot where you actually reverse polarize. So now there is more positive charge on the outside of the membrane than there is. The inside is positive relative to the outside as opposed to at rest, where it's more negative relative to the inside. Then something changes in the membrane. We go through this. And so it's an all or none type of fashion of a process. And once things go, they're going to go through a preset set of events. The action potential has an upstroke. That's a depolarization, a repolarization phase that occurs after that overshoot, and a final recovery phase where you get everything back to normal again. So one of the things that I frequently like to refer to in this is your toilet. So a toilet is a sort of a all or none repolarization phenomenon. And in fact, the analogy can get quite detailed. But if you go into your bathroom and you jiggle your handle, you can let a little water out. Not much happens. Make a little more. And then once you push it down and you get up to a certain threshold and that flapper valve comes off inside the toilet, you know it's going to flush. It's going to go through a complete set of events. And you know what else you can't do until it's finished doing that? You can't flush it again. Same sort of thing happens with an action potential. You have this all or none threshold. You have to press hard enough on the trigger for everything to go. And then when it goes, there's some machinery in there that causes it to go through a fixed cycle every time so that it's a regenerative phenomenon. And in fact, you'll find that we use plumbing analogies, or at least I use plumbing analogies quite a bit in describing electrical events. And that's really because a lot of these things, Ohm's law and such, were worked out for hydraulics before we really had electronics. Things like, you know, the control of the rudder control problem. Flow through a pipe is the same as current flow through a resistor. The mathematics of them are all the same. It's very heavily derived from plumbing. Plumbing is much more easy to visualize somehow because hydrostatics is simply height rather than trying to, the abstract concept of voltage. Charge, quantity of charge is much easier to view in terms of a volume of such. So, you know, quantity of charge would be the volume of such. Current flow is, of course, the same as flow. I mean, we use the same term, flow. So it's a volume of water per amount of time. It would be an amount of charge per unit of time. And so many of the things in plumbing make very good analogies, a little easier to visualize what's going on than the abstracts of electronics. Even though the mathematics of them are the same, it's just sometimes a little easier to use and a little more familiar with us in our day-to-day usage because plumbing in general isn't very miniaturized. So at the unit of plumbing, we have valves. A valve is sort of a hole. If you think about it in its most abstract form, it's a hole that we can open or we can close. Same thing with a channel. It's a hole. In this case, it's a pore. It's not really meant for moving water, it's meant for moving charge. And it's a charge valve. It shuts on or off in response to particular stimuli, allows flow through at a certain prefixed rate, and it's composed of proteins. So this is the topology of a voltage-gated sodium or calcium channel. They all have the same general sort of 1, 2, 3, 4 domains of the same sets of repeats. So 1, 2, 3, 4. If you look here just at the transmembrane domains, so the part that goes through this lipid bilayer. Lipid bilayers are fats. They don't like charged compounds in them, and they don't like water in them. They're hydrophobic. So you have this lipid region here that isn't going to let water or charge through. It's a very good insulator. It's very thin, but you need something to facilitate the movement through that. And so you can think of a channel as an enzyme as well, if you want to. And the reaction that it's facilitating, it doesn't actually add any energy to the whole thing. It just facilitates the movement of ions across this formidable barrier of the lipids. So it would be an enzyme that allows the transposition of a specific ion. And it has that same characteristic of enzymes, high turnover rate, lowers an energy barrier, and also has high specificity. So our channels in general, there are some exceptions, but in general, our channels have a very, very high specificity. That's why they have their names frequently include an ion. So a sodium channel is going to pass sodium. It's going to be very, very inefficient at passing potassium or calcium. A calcium channel will pass calcium and pretty much nothing else. So it discriminates between these different things while allowing for literally millions of ions to pass every second. So high discrimination, high throughput. And the structure here, 4 repeats, and within each repeat we have 6 transmembrane spanning domains, 6 of them. And these can be classified basically into 2 components. The first 4 comprise this sort of voltage sensor cassette. And in it, it has S4, which we consider to be the primary voltage sensor of the channel. So we talk about the membrane being at, say, minus 70 at rest. What does that mean in terms of how would a switch be able to tell that? Well, if you have a voltage gradient or a field, so net negative charge on the inside, net positive charge on the outside relative, you have a gradient pushing positive ions in the inward direction. So all those positive ions want to be on the inside. Well, how do you couple that to something mechanical? In particular in a protein. Well, you need charges on a protein. So what are the charge residues that are available for use on a protein? You have arginine and lysine, which are positive, and you have, of course, the acidic transporters, which are negative, glutamate and aspartate. So this S4 domain is an alpha helix, spans the membrane, and has a positive charge at every 3rd residue. It has an arginine or a lysine in it for a wide variety of voltage-gated channels. And it actually is able to sense the force across the membrane. So you have that voltage gradient. This S4 has positive charges. When it's negative, it's pushed inside. When the membrane is reverse polarized, it's pushed outside. And this is what this force and this movement of this is then transduced into this pore region here, which forms a gate and a selectivity filter. So you need to know this general structure of calcium and sodium channel alpha subunits in the heart. They're formed of 4 linked domains. And each six-membrane spanning domain, each domain has 6 membrane spanning segments. So it's got those 6 there. And on S4, you actually have fixed charge in the forms of arginines and lysines that act as the primary voltage sensor for these channels. So we have a means of taking our electrical energy and directly transducing it into physical, mechanical energy that is opening and closing this pore. And most of the biophysics of this has actually been worked out in a slightly simpler channel, simply because by its short length it was much easier to manipulate. And this would be the voltage-gated potassium channels. In each potassium channel, the gene only encodes 1 segment in general. There are some exceptions to this, but you've got 1 domain here of all of these. You have your voltage sensor cassette here, your voltage sensing domain, and then you have your pore region here, S5 to S6, and specifically in this loop, the part that forms the selectivity filter. So it sits there, it lines the pore, forms the selectivity filter for binding potassium and discriminating it and not allowing it. And not surprisingly, these channels are formed of tetramers. So you need 4 of these to come together in order to perform a functional channel. So you got 4 of them is a tetramer. S4 is still the voltage sensor, and that pore domain, S5 and S6, that's your pore domain. That's where selectivity is accomplished. So in a more detailed sort of structure, and this is taken from a simplified version of those channels that actually does not have a voltage sensor, so it's not a voltage-gated K channel. It's a voltage-insensitive one. And this is from the KCSA structure for which Rod McKinnon a few years back won the Nobel Prize of it. And it is not 4, but 2 of the membrane spanning domains. And it's two of these together in this particular plane. You can see this would be the S6 domain. This is the S1 domain. And you could see there would be another 2 sort of in the plane that bisects this out in forming that tetramer. And you see the bottom of this. This bottom region here, where it binds together, this is one of the critical gates for the channel. It opens and closes in response to the movement of that S4, or in fact in response to a couple of other things in the case of the 2 membrane spanning domain K channels. And then you see here how this loop, that H5S5 loop, it has some structure. It has this alpha helix here that comes down and then folds back up and around and onto S6, so that you have a pore domain here that interacts with these glycine side chains in the pore loop. This is what would be called the GYG domain, and forms a selectivity filter. And the structure of this selectivity filter is different if you're a sodium or a potassium or a calcium channel, and you can swap those domains out and change the selectivity of a channel using molecular biological techniques. So that's the physical arrangement of them. That S6, that sort of thing there, is often referred to as a TP. And that's a piece of jargon that requires some explanation. For people who were perhaps not raised on cowboy and Indian movies, particularly not American Indian type of movies, I found that a lot of the foreign students go, "What's a teepee?" Well, that's that long, it's a tent, and it's a fairly conical tent that the Plains Indians used around the turn of the 1800s and earlier as a shelter. And the teepee structure refers to this sort of spiral of long straight poles that could be closed or opened at the bottom here. And that's how this closes or opens. This teepee sort of tightens or loosens down there. But a teepee is what it's frequently called. It's a jargony term, but that S6 region forms a gate for opening and closing that intracellular region. And then the two membrane spanning domains form what's known as the inward rectifier families of channels. Inward rectification we'll talk about a bit more. It's fairly important. So these channels without the voltage sensor still have some special properties, are actually present in cardiac muscle, and are parts of the inward rectifier family. So how do we know about how channels behave, and how do they produce currents that look like those nice smooth action potentials we see? Now, this is a measurement device or schematic up above for something known as the patch clamp technique. Nair and Sackman won the Nobel Prize for this in the late 70s. And what they'd used was advances in integrated amplifier, op-amp technology, to actually polish glass electrodes, place them on the cell surface, grab a small piece of membrane. And this is not to scale. It's a very, very small pipette tip, and it grabs a small piece of membrane. And if they were lucky enough, they would get one, maybe two, single molecules of a channel in there. And when they had that, now remember, these are single molecules. They could take the current, every time it opens, the current's going to go through and closes, and will go through and be measured using this amplifier. Now, what does that look like? Well, it could have looked like a lot of different things, really. If you think about it, it could have opened slowly, closed slowly, or something like that. But no, it opens and closes in rather abrupt sorts of transitions. So as you might have thought for that teepee, it's either going to bam up, open, or bam shut. So very small motions there. It's a single molecule. A single molecule is very, very small. And so it is not subject really to the laws of momentum. It has essentially negligible momentum. So its movement is determined entirely by Brownian motion or thermal reactions. So it moves randomly. And what they saw were the random fluctuations. In this case, they had maybe 4 or 5 channels in here. So they would see it move, and every time a channel would open, they'd see a little more current. And they'd see more as another one opened, and if one closed, opened, closed. And this was occurring randomly with thermal motion. So they're actually looking at the Brownian motion of a single molecule occurring in real time as they moved. And they had more than one channel here as it went open and closed. But you can see it. It moves very suddenly. It's either occluded or not occluded. That pore is sitting there, occluded or not occluded. They open and close randomly. Well, that doesn't sound like a system you can generate action potentials and sort of predictable behavior out of it. But when I say randomly, I don't mean randomly as in 50-50 chance of being open all the time or closed. It's biased odds. They're biased by chemical potential. And if you have enough channels, they will adopt a predictable behavior. So how many of you guys have gone over to the casinos, say on the Niagara Falls? Fair number. So, any of you play the slots? So, the slots are a random game. They're legally mandated to be random. But they're not random without a bias. They have a bias to them. So you know that if you pull the handle long enough, you're going to lose money. You may be gambling with the casino, but the casino is not gambling with you. And this is part of the laws of statistics. So they have a bias to them. Every time you pull the lever, I think on the best games, if you've bet $1, you are on average going to lose a nickel. But every time you do it, you don't necessarily lose a nickel. In fact, you can't lose a nickel. You would either lose $1 or you'd make some, portion of that back, or some multiple of it back. And it happens randomly, but it happens randomly with a bias. But if you have enough of them, so this is why they have those banks and banks of machines, and they have to get a certain number of people in there. Their losses become very, very predictable. The variability of a random process, if you start to sum enough of them, will go down as the square root of the number of poles, for instance, that you have on that. So when you have a large number of channels, they start to adopt a very smooth type of behavior here. And that smooth behavior is what gives us our overall sort of behavior. Now, that's nice, but we got a couple of different types of channels. Why do we have different types of channels? Well, we need them to do different things at different times. So our classic action potential here shows your membrane potential. Now that's just the sum of the charge that goes across the membrane. Because remember, the charge on a membrane is the charge on a capacitor. You have that cell membrane capacitance there. That is the cell membrane. It's a non-conductor that's surrounded by two conductors. Conductors being the cytosol. Cytosol is very conductive in the extracellular solutions. Saline solutions are very conductive. So you have two conductors separated by a small dielectric. And you charge and discharge that by the ions that go through. So you see the rapid upstroke of the action potential here. You see the conductance of the sodium current. This is G. What is a conductance? Conductance is what biologists use instead of resistance because it makes our lives a little bit easier. So when you see this figure and you're reading these sections in the text, G is a conductance. If you remember Ohm's law, voltage equals current times resistance. A lot of times we don't really want to calculate what the voltage is. We want to calculate what the current is. And so I equals V over R. Well, V over R comes sometimes a little difficult to deal with. So we just take G, and G is just the reciprocal. 1 over R is G. So it's the total membrane conductance. So as the conductance gets big, you get a little change in voltage, you get a lot of current. If the resistance gets big, it's just the opposite. You get a little current for not much change in resistance. So conductance is useful because it adds directly when in parallel. And since all of our channels are in parallel across the cell membrane, they add very nicely in their conductances, whereas with resistors, it would be adding reciprocals, and it's just a problem. So you see the conductance of this turns on its highest actually up here near the peak. It's not highest here where the dV/dt is highest. Why isn't it highest there? Because your dV/dt, your charging or discharging of that capacitor, your cell membrane, is a function of how much current is actually going through. And so that's a product of this times the difference between, say, ENA and your membrane potential. You get too close to ENA, as you are here, it doesn't matter. High conductance is still not going to give you much current, so your dV/dt is small. GK, similarly, is the difference between the K, or the current will be the difference between the K and the, between EK and the actual membrane potential. So you have firing of sodium early and then potassium later. There's something missing on this. What's missing on this? In order to fire an action potential, you need a stimulus. So there's a stimulus that's missing on this, but it's not much problem for it conceptually. but it is important to know you don't get an action potential without a stimulus. And so in the squid axon, the action potential is mediated by the sodium current. It's fast, it turns on quickly. So it turns on first, turns on quickly, brings it up as far as it's going to go. K turns on, potassium channel turns on with a delay. So you see it opening up here. So by opening up, I mean that the average number of channels open at any time is starting to increase. And they do that with a delay. And then you see the sodium conductance goes back to 0 pretty quickly, sits down at rest. But you see this GK takes a long time to reset. So there's a lag after which the system resets. And that gets us to two fairly important concepts in understanding reentry, which we'll go over later, but you need to know the terminology about this. We have an absolute refractory period, and we have a relative refractory period. So the absolute refractory period is here. It's early on in that action potential. And why can't you fire an action potential there? Well, the reason you can't fire an action potential there is you're already firing an action potential. The sodium currents are open, everything is going. There's not much chance of firing one because everything's firing. As you get later, things start to reset. And it's during that resetting process we have what's known as the relative refractory period. You can elicit an action potential there, but it will not be normal, and it will require a much larger stimulus in order to do it. So you need to know those terms. Absolute refractory period, an additional stimulus, just can't do anything. It just, it'll depolarize the membrane a bit and change things, but it will not elicit an action potential. The relative refractory period is basically an sort of period. You can elicit an action potential, but it's not going to be quite right, and you have to work pretty hard to do it. So the cardiac action potential itself is a little more complicated than this simple interaction, but it does have those two properties. Each region of the heart has different cell types. You start out with your pacemakers, where your heart starts beating first. You have your atrium that have to contract at this particular rate. You have the AV node, which gives you some block, and you have the ventricles, which are doing the work. And the size and the shape of each of these action potentials, both its duration, its rate, where it sits on the resting membrane potential, is all important for understanding and predicting and giving you function. And that's because the action potential, and if I emphasize something as many times across lectures as this, the action potential shape of a cardiac action potential controls your rate of development and relaxation of contractile force. So your action potential, you have calcium entry all through the plateau. It's developing contraction. And then when you repolarize, you have that calcium being pumped out. And it's only after you start relaxing that you start to reduce your contractile force. You can relax and refill your chambers of your heart. Excuse me. So, the book has classified two types of action potentials in it. Fast response action potentials and slow response action potentials. These could have been done using different terminology that you will find in the literature and elsewhere, in that these would be considered to be working cardiac cells and specialized conduction systems and nodal cells. So you have fast response, that would be ventricle, atrium, those are your working myocardium, and also then the his Purkinje, which spreads the rapid excitation. Slow response is pretty much SA node, sinoatrial node, and AV node. And it has a slow response, as you might expect. But what do they mean by a slow response? Well, couple of things. The first being what the action potential looks like. You have an upstroke here, phase 0 of the action potential. If you look at the fast versus the slow response action potentials, this upstroke, dV/dt, is orders of magnitude faster than this. That's because the nodal action potentials are, the upstroke is dominantly governed by calcium channels, not by sodium channels. So you have sodium firing, and then you have calcium firing. You also have some complicated notch type behavior here involving the interaction of transient outward currents and a plateau phase, pronounced plateau phase, rapid repolarization, and finally your ending. The slow response ones, you skip the sodium and most of the transient outward stuff here. So you have a fairly slow, smooth repolarization, very triangular type shape, and you have a corresponding. But you still have an effective refractory period. Now, effective refractory period, a little different terminology than we just used for the sodium channel. Don't let it confuse you. It's the same thing. Effective refractory period or absolute refractory period. You're not going to be able to fire an action potential during those times because you're already firing an action potential. You're not going to be able to flush your toilet during that time because your toilet's already flushing. A little extra stimulus just isn't going to add that much to it. You get to the bottom and you can get a weak flush if you hold it down long enough, sometimes if you're lucky. Same thing here, is sort of the system is resetting itself. That's what that means. And so that's called a relative refractory period in cardiac muscle. So two different sets of terms for basically the same thing in two different tissues. And the cardiac people don't talk all that much to the neuronal people in certain circles. So both of them persist in literature. You need to know both of them and realize that they're basically the same thing and can be used to refer to either cardiac or a neuronal action potential. So you have these rapidly depolarizing action potentials. They're mediated by sodium currents. The slowly depolarizing action potentials have much smaller calcium current with slower kinetic tissues. And these slow tissues are nodal tissues. They have these calcium-mediated action potentials. So let's put it together for what happens in an action potential here. We have a cell at rest. Now there's some errors on these figures that are in your textbook, so people invariably get confused about them. Potassium is exactly balanced at rest by electrostatics. So you have some potassium going out at all times. There's a small inward leak current that goes on at rest. So the sodium-potassium pump is always pumping that extra bit of potassium out. Sorry, that extra bit of potassium in, and as it's balancing, you have your electrostatic gradient sitting at the resting membrane potential. So the resting membrane potential, where the membrane potential where these two exactly equal, is through the Nernst potential. The Nernst potential is this expression down here, 61.5 log K plus I over KO. There are a lot of different forms for this. Don't let them confuse you. The Nernst potential can be seen in a lot of different forms. Some don't use log base 10. Some use natural log. Then the number in front is different. Some of them will use RT on F, the universal gas constant, and temperature in Kelvin over the Faraday in front of the log term there. And again, using a natural log, not a regular log. Sometimes it'll be KO over KI, in which case there'll be a negative sign that's there in this case and it will be gone in the other one. So there are a bunch of different forms for the Nernst potential. Just be able to recognize this, the log ratio concentrations by some constant. I don't expect you to memorize all the different constants, but I do expect you to know that the basic form of this equation, recognize what it's useful for. It's useful for understanding when you have K here, it's at a high concentration, it wants to go to a low concentration. That's diffusion. So diffusion, you have K, it's at a high concentration, the random motion of those particles, they're going to want to diffuse over to the lower concentration range. You can bias that random walk or that random distribution by putting a force on those positive ions. That force will be equal and oppositely directed when there is no net movement of K. Where there is no net movement of K, those two are equal and opposite. You will be at your Nernst potential. So the Nernst potential is how you convert from chemical potential to electrostatic potential. Equal, opposite balancing. That's where you carry no net K current. Does that mean that no K is going to cross the membrane? No. K is going to go randomly across it, but it's going to go across in equal amounts by random. That's occasionally a hard concept for people, but when you're doing a tracer flux study, it's important. You're not actually measuring net flux. You are measuring total flux. And so there will be no change in the K concentration, but K will be exchanging across the membrane. It's going back and forth thermally. You can't stop the random movement of K. You just simply have it so that that random movement is not biased in either the inward or the outward direction. So the Nernst potential is this equation here. Comes in a lot of different formats. You should be able to see it. It sets the resting membrane potential. Now that's not to say that it is the resting membrane potential. This is an important thing that people have trouble with. The resting membrane potential, remember that earlier slide we saw with the balances of all that current. The resting membrane potential, that where the membrane sits all by itself, is always above the Nernst potential for potassium. There's always some net movement of potassium out because there's always some leaking background inward currents and transporters that are operating at rest that need to be balanced. So there's always a net balance that keeps the resting membrane potential above the Nernst potential for potassium. Okay, so there's an important thing to know. There's the Nernst potential, which is this theoretical 0 point. It's calculated, it's a thermodynamics absolute, and then there's what the cell actually does, which is sit slightly above that. And it does that because it does more than just conduct potassium. It has other things going on there. So that sets us up then for what goes on during an action potential. As we go through the phases of an action potential, we get a stimulus. Always need that stimulus to get us started because it's something to move us enough positive on the inside to start putting some force on those alpha helices of the sodium channel. When that happens, and that sodium channel starts to open, we get a big current. And that big current is sodium, and it just diffuses into the cell. And that's what causes our phase 0 or rapid depolarization. You go up, you actually reverse polarize, you get near the sodium reversal potential. You don't ever go to the sodium reversal potential. Why is that? Because there's always some other currents there that are conducting outward currents that will keep you from actually reaching the sodium reversal potential. So you end up going up plus 40 or so, overshooting, reverse polarizing the membrane so that the inside now is positive now relative to the outside. At this point, you have this notch phase, or phase 1 in many action potentials. Not all of them. You have this phase 1, and there's a transient opening of potassium, particularly this ITO, or the transient outward potassium current. And it conducts K in the outward direction. So you have K moving in the outward direction in this notch. Well, eventually, calcium currents also turn on. Now, this calcium current here has some fairly funny arrows. calcium never ever diffuses out of the cell. Calcium goes in through the L-type calcium channel, and that's it. It will not go out through the calcium channel. There's no way that you will be above, at any point, the calcium Nernst potential. I'm not sure why the book has this here. It may denote the fact that there are some exchangers and such which change direction at some point in the whole process, but I don't know. It's very confusing to a lot of students here. Calcium comes in through the L-type calcium channel. It never goes out. Similarly, potassium is always an outward current. It never actually goes inward in the cell. Because its reversal potential is below the resting potential, and the sodium is always above whatever the peak is. This is the calcium. So calcium never actually goes inward. But you have the two of these sort of balancing here, and they sort of fight, essentially. You have an inward current and an outward current. The net current, then, is very close to zero. If the net current is very close to zero, you get very little change in the net voltage. Finally, the calcium current inactivates, potassium wins out, you have this repolarization here. There's a sodium current here, drawn here. Again, very, very confusing here, and I'm not sure that what they meant by this. There is a defect in human sodium channels where there is a late sodium current that can become active in this region. In general, it's only a significant current, at least for us, if a person happens to have one of these long QT intrinsic sodium channel defects. So really ignore that. It's K channels turning on, dominating this repolarization. And then here we have sodium going in and out. That's just wrong. At rest, you don't have sodium just going in and out. Sodium is basically, permeability is very, very low. There's a little bit of it in that background leak current. You have the K currents going out. It's essentially dominated by a large K conductance. It's very near EK, always slightly above EK, because you do have some background sodium currents, but you have K currents here that are active. The bottom part is a little more accurate. You have K currents that are active, and it really sits down near EK, and the dominant conductance is outward potassium currents with a small sodium current conductance. So the action potential is a complex event. It's got a lot of timing of these channels that goes through it. For most of the cardiac cells, except for those slow nodal types, the sodium channel usually dominates the action potential. You actually have calcium that's flowing throughout most of that action potential, and it's because it's integrating over that time and into those regions that you have this part of why you have this control over relaxation. And then potassium turns on slowly and eventually dominates when you return to the resting membrane state. So what's our official quit time? What? 10:50. Oh, okay. In that case, we will go over gating of the gating particle movements next time. Thank you.